Have you ever heard of synthetic aviation fuel? Do you know how it's made? Welcome to the fascinating world of sustainable aviation fuel, or SAF for short. It's the new kid on the block in the aviation industry, but it's quickly becoming a key player in the quest for more sustainable air travel. SAF is a type of synthetic fuel designed specifically for airplanes. But what sets it apart from the traditional fossil-based jet fuels we're all used to? Well, in a nutshell, it's all about sustainability. SAFs are derived from renewable resources, which means they can help reduce our reliance on fossil fuels and cut down on greenhouse gas emissions. And let's face it, in a world where climate change is a pressing concern, every little bit helps. Now you might be asking yourself, how is this synthetic fuel made? Well, it's not as simple as just squeezing some oil from a plant or collecting waste from a city. The production of SAF involves a series of complex chemical and engineering processes. It all starts with the selection of a feedstock. This can be anything from plant oils and agricultural residues to municipal solid waste or even carbon dioxide captured from industrial processes. The chosen feedstock then undergoes a series of steps including pre-processing, gasification or pyrolysis, gas cleaning, Fischer-Tropsch synthesis, and hydroprocessing before finally being blended with conventional petroleum-based jet fuel to create the final SAF product. And that's just a simplified explanation. Each step in the process has its own set of challenges and requires a deep understanding of chemistry and engineering. But the end result is a fuel that not only meets the necessary quality and performance standards for use in commercial aviation, but also helps to mitigate the environmental impact of air travel. Intrigued? Let's delve deeper into how this eco-friendly fuel is made. Together, we'll uncover the science behind SAF, the challenges involved in its production, and the potential it holds for a more sustainable future in aviation. So fasten your seatbelts and prepare for takeoff as we journey into the world of synthetic aviation fuel. The first step in the process of making synthetic aviation fuel, or SAF, is feedstock selection. The feedstock is the raw material that will be transformed into fuel, and choosing the right one is crucial for the efficiency and sustainability of the process. Let's delve into the different types of feedstocks used for SAF production. The first and perhaps most common type is biomass. This can include plant oils, agricultural residues, or waste fats. Biomass is a renewable resource, and using it as a feedstock not only helps reduce waste, but also contributes to the circular economy. Next up is municipal solid waste. Yes, you heard right. The stuff we throw away every day can actually be converted into jet fuel. This includes everything from food scraps to paper and plastic. By using waste as a feedstock, we're not only finding a use for materials that would otherwise end up in a landfill, but we're also reducing the demand for virgin resources. Last but not least, we have carbon dioxide captured from industrial processes. This might sound a bit futuristic, but it's already happening. Industries generate a lot of carbon dioxide, a potent greenhouse gas. Instead of letting it escape into the atmosphere, we can capture it and convert it into fuel. This not only helps reduce greenhouse gas emissions, but also provides a new source of feedstock. When choosing a feedstock, two key factors come into play: sustainability and availability. The feedstock should be renewable or reusable to minimize environmental impact. It should also be readily available to ensure a steady supply. It's worth mentioning that the choice of feedstock can vary depending on the region and specific circumstances. For instance, a country with abundant agricultural waste might choose to use that as a feedstock, while a city with a high volume of municipal waste might opt for that instead. Having selected the feedstock, we can now move on to the next step. After the feedstock is chosen, it undergoes pre-processing. This step is crucial to prepare the feedstock for conversion. The process is quite similar to making a gourmet meal. You wouldn't want to cook with dirty vegetables, would you? Similarly, feedstocks often need to be cleaned to remove any impurities. This could involve washing, scrubbing, or even a chemical bath. Next, the feedstock is dried. Just as you'd pat your fresh produce dry before cooking, the feedstock needs to have any excess moisture removed. This is usually done through a process of heating or exposure to air. The last step in pre-processing is a bit like marinating your ingredients. Sometimes, the feedstock might require chemical treatment. This helps to break down any stubborn impurities and makes the feedstock more suited for the conversion process. So you see, feedstock pre-processing is all about preparing the raw material for the main event. Once the feedstock is processed, it's ready for conversion. The processed feedstock is now converted into a synthesis gas, or syngas. This transformation occurs through two primary methods, gasification or pyrolysis. But how exactly does this work? Let's find out. Gasification is like a well-choreographed dance, where the feedstock and either oxygen or steam are the main performers. They are heated together, and through the magic of chemistry, they transform into a mixture of carbon monoxide and hydrogen, the components of syngas. It's a high-energy process that takes place in a controlled environment, ensuring the right conditions for the conversion. On the other hand, pyrolysis is more of a solo act. Here, the feedstock takes center stage. It's heated, but in the absence of oxygen. This process leads to a trio of outputs: gases, liquids, and solids. The gases produced are a part of the syngas we're after, while the liquids and solids can be further processed for other uses. Both gasification and pyrolysis are like turning raw ingredients into a gourmet meal. They take the humble feedstock and transform it into something far more valuable, a key ingredient in the recipe for synthetic aviation fuel. These processes are not just about heating things up, though. They're precise, calculated, and above all, efficient. Every step is designed to maximize the conversion of feedstock into syngas. They are the result of years of research, engineering, and innovation, all focused on one goal: producing a sustainable alternative to fossil-based jet fuels. So why go through all this trouble to produce syngas? Well, syngas is the precursor to synthetic aviation fuel. It's the building block from which long-chain hydrocarbons, the heart of synthetic jet fuel, are made. Without syngas, there would be no synthetic aviation fuel. But we're not done just yet. Once we have our syngas, it's time for a bit of housekeeping. Like any process, gasification and pyrolysis can introduce impurities, and we need to ensure our syngas is as clean as possible before moving on to the next stage. With syngas in hand, it's time to clean it up. The syngas, while crucial, isn't quite ready yet. It contains impurities that need to be removed. At this stage, we're dealing with a cocktail of gases that, while rich in hydrogen and carbon monoxide, also carry unwelcome guests. These impurities take the form of sulfur compounds, nitrogen compounds, and trace metals, elements that we don't want in our final product. So how do we clean up this syngas? Through various purification processes, each designed to tackle specific impurities. Some methods include absorption, where the impurities are soaked up by a liquid or solid absorbent, and adsorption, where impurities adhere to a solid surface. Other techniques involve chemical reactions that transform these unwanted substances into harmless byproducts. These steps are vital to meet the required quality standards for aviation fuel. It's all about ensuring that the syngas is as clean as a whistle, primed and ready for the next stage. Now that the syngas is cleaned, we can move to the next step, Fischer-Tropsch synthesis. Next up is Fischer-Tropsch synthesis, a key step in creating synthetic aviation fuel. The Fischer-Tropsch synthesis, or FT synthesis for short, is a key chemical process in the production of synthetic fuels. It's been around since the 1920s, named after the German chemists Franz Fischer and Hans Tropsch, who first developed it. At its core, the Fischer-Tropsch synthesis takes the clean synthesis gas, or syngas, and transforms it into long-chain hydrocarbons. These hydrocarbons are primarily straight-chain alkanes, also known as paraffins, which form the basis of the synthetic jet fuel we're aiming to create. So how does this transformation occur? The magic happens when the syngas is reacted over a catalyst under specific temperature and pressure conditions. The catalyst, which can be made from a variety of materials including iron or cobalt, plays a crucial role in this process. It drives the reaction between the carbon monoxide and hydrogen in the syngas, facilitating their reassembly into the desired hydrocarbons. In essence, the Fischer-Tropsch synthesis is like a molecular construction site. The carbon monoxide and hydrogen are like the bricks and mortar. The catalyst is the construction worker, and the hydrocarbons are the finished building. The catalyst worker takes the syngas materials and, under the right conditions, assembles them into the hydrocarbon structures we need. Despite its age, the Fischer-Tropsch synthesis remains a crucial process in synthetic fuel production due to its ability to produce a wide range of hydrocarbons from a variety of feedstocks. Its flexibility and adaptability make it a key tool in our efforts to produce sustainable aviation fuel. However, as crucial as the Fischer-Tropsch synthesis is, it's not the final step in creating synthetic aviation fuel. The hydrocarbons it produces are still raw and unrefined, They're like rough diamonds that need further processing to become the sparkling gems we need them to be. We're not done yet. The hydrocarbons need additional processing. The hydrocarbons produced by the Fischer-Tropsch process undergo further processing through hydroprocessing. This step is crucial in refining the properties of our synthetic aviation fuel and ensuring it's up to the high standards required for commercial flight. Now, what exactly is hydroprocessing? Well, it's a series of processes designed to improve the properties of the fuel and remove any remaining impurities. It typically involves two key steps: hydrotreating and hydrocracking. Let's start with hydrotreating. This process involves treating the hydrocarbons with hydrogen in the presence of a catalyst. The purpose here is to remove unwanted elements like sulfur, nitrogen, and oxygen by converting them into hydrogen sulfide, ammonia, and water, respectively. All of these are easily separable from the fuel. In addition, hydrotreating also helps to stabilize the fuel by saturating any unsaturated hydrocarbons, reducing the risk of undesirable reactions. Now onto hydrocracking. This step is a bit more complex. It involves breaking down the long-chain hydrocarbons into shorter ones, again using hydrogen and a catalyst. But why do we need to do this? Well, shorter hydrocarbons have a higher cetane number, which is a measure of the fuel's ignition quality. A higher cetane number means better combustion efficiency and lower emissions, just what we're aiming for with synthetic aviation fuel. These processes aren't just a one-and-done deal, though. They're carefully monitored and controlled to ensure the fuel has the right properties. Things like temperature, pressure, and the hydrogen to hydrocarbon ratio are all crucial factors that need to be just right. It's a bit like baking a cake. You need the right ingredients in the right amounts, mixed together in the right way to get the best result. So through hydroprocessing, we're able to fine-tune our synthetic fuel, improving its stability, enhancing its performance characteristics, and removing any remaining impurities. It's a vital step in the journey from feedstock to flight. Now that our fuel has been processed, it's time to blend. The final step involves blending the synthesized hydrocarbons with conventional jet fuel. This stage is crucial as it determines the final product's properties and its suitability for use in aviation. The synthesized hydrocarbons aren't used purely on their own. Instead, they're combined with regular petroleum-based jet fuel in varying proportions. This blending is a delicate balance, a meticulous process of mixing and matching to create the final sustainable aviation fuel, or SAF, product. The precise blend ratio depends on a variety of factors. These include regulatory requirements, technical specifications, and economic considerations. For instance, regulations may stipulate a maximum percentage of SAF that can be blended with conventional fuel. Technical specifications might dictate the blend ratio based on properties like energy content or freezing point. And of course, economic factors such as the cost of the synthesized hydrocarbons and conventional jet fuel also play a part. Once the blending process is complete, we're not quite done yet. The resulting SAF blend must undergo rigorous testing and certification. This is to ensure that it meets the necessary quality and performance standards for use in commercial aviation. The certification process is comprehensive. It covers a wide range of characteristics, including the fuel's energy content, freezing point, flash point, and more. But it's not just about ticking boxes on a checklist. The certification process also includes extensive engine and flight testing to verify that the SAF blend performs as expected under real-world conditions. Remember, SAF isn't just an alternative to traditional jet fuel. It's a solution that aims to reduce greenhouse gas emissions and mitigate the environmental impact of air travel. So it's crucial that it not only meets, but exceeds the standards set for conventional jet fuel. And there you have it. That's how synthetic aviation fuel is made. From selecting sustainable feedstocks through complex chemical processes and engineering feats, to blending and certification, every step is designed to create a viable, environmentally friendly alternative to fossil-based jet fuels. Let's recap what we've learned about synthetic aviation fuel. We've delved into the intricate journey of this eco-friendly fuel, starting from the careful selection of a sustainable feedstock. This feedstock undergoes pre-processing to prepare it for conversion, which is carried out through gasification or pyrolysis. The resulting synthesis, gas or syngas, is then cleaned to remove impurities before being subjected to the crucial Fischer-Tropsch synthesis. This process transforms the syngas into long-chain hydrocarbons, the building blocks of our synthetic jet fuel. But it doesn't end there. These hydrocarbons are further refined through hydroprocessing to enhance their properties and ensure they're fit for flight. Finally, the synthesized hydrocarbons are blended with conventional jet fuel, rigorously tested and certified for use in commercial aviation. This complex process offers a promising alternative to traditional fossil-based jet fuels, playing a key role in reducing greenhouse gas emissions. Thank you for joining us on this journey into the world of synthetic aviation fuel. Until next time.